Um, so my talk primarily focuses on forensics, but we have applications in other areas of security as well. But primarily for forensics, much of the valuable information that an investigator might want to have is currently not available. And this is partly due to the fact that the information simply isn't there, or it's not there and it's not recorded, or it could be that it has to be derived by correlation, which can be tedious and error-prone. So during this talk, I'm going to raise a question of what the desired information actually is when performing a digital investigation. And in the second part of my talk, I'm actually going to focus on two of these pieces of information, which is user influence and location information. So in the first part, I'm just going to explore a little bit of what kind of information do we actually want of a system as a forensic investigator. Then I'm going to introduce a model that uses labels to track information on a system, present some case studies about that, discuss the implementation, and then conclude and present some future work. In digital forensics, usually you're concerned with retrieving and analyzing digital evidence. And existing tools focus primarily on the actual retrieval of that information. And that is a pretty straightforward goal, because you have to see what you can get off the system, what's actually there in order to analyze it. But apparently, nobody has asked the questions, what kind of extra information would you want to have, if you could, for a forensic investigator to make your investigations more easy? So usually the information retrieved from a system is either stored on the file system metadata itself or in the logs. And given that information, you basically only have a small snapshot of the system. You cannot really determine some of the answers of questions you would like to have asked, you would like to have answered. There we go. So before I actually go into the area of what the information is that we want, here's a quick classification of the desired information that is either there or not there. So the first category is information that is available on a system and is actually recorded explicitly on non-volatile media. And an example of this would be the file access modification and change times of a file system. In the next category, we have information that is available, but it's not explicitly recorded. For example, this could be the user ID of the person who modifies a file. The system knows about it, but when actually an operation on a file is performed, this information is not recorded anymore. The next category is information that is not available to the system, but that we can probably make available. And an example of this might be location information. Current computing systems do not really have a sense of what location is, but one can make some of that probably available. And the last category is information that we might want, but it's actually impossible to be obtained. And I'm actually going to get into that aspect a little bit later on. So what do we want as a forensic investigator? And of course, it really depends on the kind of investigation that we are doing. It could range from simply locating contraband material to a full-fledged investigation of a break-in, trying to figure out what happened. And in the most general case, we want answers to all these questions. Who did what, from where, when, how was it done, and why was it done? And I threw in the why there, but usually you have to answer all the other questions and then make a guess as to why the attacker or criminal or who knows what did his actions the way he actually did. So now I'm just going to go through most of these and give suggestions explaining why we want the information and give suggestions as to how we can rectify this. I'm not going to pretend that I'm going to solve all these things, but I'm just going to discuss what is wrong with some of the existing information and what we can do about it. So the first question is the when, and that's an easy one. Because most file systems actually carry timestamps. They're called MAC times, which stands for modify, access, and change times. And they're being stored as metadata of the file system. However, MAC times simply emerge from the need for different tools, like archiving tools, backup tools, compile tools, and all that. And actually, there's no really standard for any of those. So on different systems, you actually have different kinds of files of timestamps. For example, on Windows NT, on NTFS, you have an explicit creation time, which Linux does not have. Linux has a delete time, which Windows does not have, and so on. Plus, we have misleading names of the timestamps. Sometimes the C part of the MAC time is called a create time, but in essence, it's really a change time. It is updated when the metadata of the file actually changes, which initially is a creation time. But if you do things like change permissions on the file, then that change time is updated also. Plus, timestamps are very easily changed. There are userland tools you can do. There's a touch command which changes the access time, the change mod time, changes the change time, the C part. You can edit a file to change the modification time and so forth. And in addition to that, only the latest operation, only the timestamp for the latest operation is kept. So everything that was before that is gone. So what can we do about the when part? First of all, you should have standard timestamps available on your system, which should include a create, a delete, an access, a modify, and the change time. Then these timestamps should not be subject to alteration from a user, which means that the system has to keep us and they can't be modified. And if you still need timestamps that the tools I mentioned, the backup tools, or whatever tools they need, then you can have extra timestamps in userland that fulfill that role. And the last point is, ideally, you want to keep timestamps for all operations that took place. Now, this can take space because many files are accessed quite frequently or other files are modified frequently. But you can categorize things. If you have files that you do not expect to be modified in a frequent manner, you can log the modification times for that, and if there is frequent activity, that should stand out. The same goes for access for certain files you don't expect to be accessed all that much. And all of that depends on the system policy. So the next category of information is the how question. So how did things happen on a system? And basically, I want to ask which programs were used to perform an action on a file. And it should make a difference whether notepad.exe was used or a program called backdoor.exe in order to create a file, for example. And these programs act on behalf of the user, and I call them controlling agents. And there can be a chain of those. So you can have a chain of programs executed and then perform an operation on a file. So for example, from the command line, you invoke the Explorer, which then calls winamp to play an MP3 file. And ideally, again, we want to store the entire chain of those agents for file operations. And again, space considerations are an issue here. What happened? So if you modify a file, then what was the actual nature of the change? Usually, you just know it's been modified at this time, but what was actually done to the file? especially if executables were replaced, what's the contents for, what's the actions of the new executable. So you could do that by storing hashes, if space is of concern, of each program that executes an operation on a file. And then later you could piece that back together to known versions of good files, or even known versions or known hashes of malicious files. Or you could store the entire nature of the change of the file within the metadata, sort of keep a delta list of changes that were performed on a file. And once again, space is an issue here, and it depends on how much space you're willing to devote to this, and you also need a policy of what you do when you run out of space for all these. So coming to the more interesting, at least to me, questions are, who is actually responsible for actions on a system? So many systems, except for MS-DOS, usually have a notion of a user on a system, and they're being assigned some sort of identifier at login. And the reason the user IDs are there lie primarily in access control. There's a set of permissions stored with the file, and there's a set of permissions stored with the user, and only a process who has the right permissions can execute or access the file. So what is called the owner of a file doesn't have to necessarily be the person who actually created or modified the file, which from a security standpoint is not really that satisfying. Sometimes you can make deductions about who was doing things to a file by correlating log entries, like this user logged in between 8 and 9, and the file was modified at 8:40, and you can make a guess that it was probably this user who did stuff to the file. But how can you know for sure? So you might say, well, since we have all this timestamp information, we can just record the user information with the timestamp as well, and we have solved the problem. But it's unfortunately a little bit more complicated than just that. So for example, in this scenario, user A reads the contents of file 1, then uses inter-process communication to convey that content to user B, who creates file 2 from the contents there. And if we look at file 2 now and its metadata, then we only know about user B having anything to do with it, and its creation and its contents. And the entire notion that user A actually played a crucial role in the creation of this file is lost to the system. So we can't really just stick the timestamp of the user ID of the process who did stuff in there, and then we're done. And I'm going to get back to this a little bit later. Yes?
The user should be the process, right? Which is the controlling agent in the graph, and user A and user B.
They are what?
The user should be the program or the controlling agent in your term.
Well, ideally you want both, right? You want to have the idea of the user as well. You don't simply just want the program that created it.
Since I actually remember the IPC will be used for intercommunication between processes.
Yes. Yes, if the circle we can see as the process used by user A, I don't know, or user A logged in, and then it's the user ID associated with that process at this point. Yes, ideally we want to record all this stuff I earlier mentioned, but right now I'm just focusing on the identity part. The last interesting piece of information is actually, where did things come from? And by this I mean both the origin of files as well as the location of where a user actually might be when controlling a process, meaning from where did he log in. So some systems keep incomplete information and really not satisfactory information about this. For example, on Unix systems, you have the utemp file, which is set when a user logs in, but it only stores a string of the network location of the user, and it's of fixed size, so it's frequently truncated, and it's stored in a file, which is subject to modification as well. Plus, there are some third-party extensions. TCP wrappers is an access control mechanism for network servers, which allow you to allow or deny network connections based on IP addresses and ports. Globally unique identifiers were introduced to be part of Word documents or Office documents, which contain a timestamp and the location information. So as these get passed along the system, you at least know from where they originated. And Dorothy Denning has a, I think it's a proposal still of utilizing GPS information for access control on the system. But none of these things are actually part of the system. They're third-party extensions. Plus, they're only being used at the perimeter of the system to perform access control decisions. Once you're inside, there's no notion of a location anymore, except for whatever you have in that UTemp file, which is associated with the process. So suppose we are able to just get the origin of files as they come into the system. So we have a compiler that was part of the operating system initial distribution from the CD-ROM. We downloaded some library from some website. The user typed in some C code at the console, and later on he logged in from a remote location and compiled the C source file into an executable. So even if we are able to classify the initial location of files, what should the location of this file be? And ideally, we want to still have a notion of all these different locations playing a role for the new location or from where that file actually came from, this executable. So now I'm going to come back to these past two examples and kind of motivate my thesis research with that. So in both cases, we have basically information flowing from entities on the system. And in this example, information was flowing to the process controlled by user A from the file. Then the information was propagated to user B, and finally into file 2. Same here, all the information from the different files was combined in the session with the compiler, and that information was flowing again into the executable. So we can basically use information flow analysis to make some sort of assertion of either what caused the creation of file 2 or which sources were used to create this new file. However, if we use information flow analysis, we have the problem that we basically have an entity here, and we can observe its inputs and outputs. And we are supposed to make some projection about the relation of the inputs and outputs. If we use static information flow analysis, we basically analyze all the possible programs that can run, and we have a glimpse of what's going on inside here, and we can make that decision. Static information flow analysis is concerned with analyzing the source code of a program and then determine how information actually flows. But it's limited in the respect that you can only execute those programs that you have analyzed on the system in order to make a good case. And this might not be acceptable in every situation. Then there's dynamic information flow analysis, and usually dynamic information flow analysis is concerned with actually looking inside of this entity here and trying to figure out what's going on. Because the problem, if you treat that as a black box and you don't know anything what's going on inside and you only can observe inputs and outputs, it is actually undecidable to make a statement whether input 1 or input 2 is responsible for the output. So my hypothesis is that I don't want to find out what's going on in here because this is expensive as well in terms of performance and maybe storage requirements. So my idea is I don't care which of these two is responsible for the output. I'm just going to say both of them are. And therefore, my idea is to bind a meaningful label to a principle on the system, such as here, and then propagate this label as information is being exchanged to other principles or objects on the system. And the actual nature of the label right now is not important. I'm going to go to that in the case studies a little bit. Now this graphic is a little bit misleading because it makes you think maybe that ooh, it was I2 that caused this output. In essence, it might have been I1, and this is where false information gets propagated too. Even if there's not a label associated with that principle there, it might have actually been I1 who caused this output. In this case, A is not really the way the information was truly propagated, but it could have been I2. And this is important information as I will show later for an investigator. So basically, input and outputs are conveyed through channels on the system. If you have principles communicating with each other, and I'm just going to quickly address what Lamson defines for his 3 categories of channels. You have data channels, which are regular channels where you read and write to, and they're intended for information exchange on the system. It's going to be reading, writing to a file, to a pipe, to a socket on the system, all those things. Then we have storage channels. Storage channels utilize shared resources on a system to convey information. And this could only be as small as 1 bit at a time. And an example of this is testing for the existence of a file. If 2 parties have a shared file somewhere and you agree on certain time intervals to check whether the file is there or not. So in time interval 1, first party creates the file, second party reads it, that's the 1 bit. Next time interval, maybe he deletes it, checks it's not there anymore, that will be the 0 bit. So you can convey 1 bit of information in each time interval that way. And this is what Lamson calls a storage channel. And then there are covert channels, which are channels that are not intended to convey information at all on a system. And this could be things like increasing and measuring system load. And you can use the same kind of example in each time interval. If a user generates a lot of system load and the other one measures it, that's the 1 bit. And if there's no extra system activity, that's a 0 bit. And those are covert channels. The data and storage channels you can determine on a system by using a shared resource matrix. And that was proposed by Kimmerer, and I'm not getting into that in any more detail. So basically, you can identify those channels. Whereas for covert channels, it's usually not that easy to do so. And I will not consider covert channels in the remainder of this work. So given that I want to bind a label to a principle and then propagate it, I have a basic model. We have a set of labels, a set of active principles, and a set of objects and channels between principles and principles, as well as principles and objects. There are label sets associated with all the principles, the objects, and the channels themselves. And we have some sort of update function that updates labels as information is being exchanged. I have the following operations, and I'm not going to go into too much detail here. Basically, we have the adding of a label, the creation of our subjects on the system. Then we have opening and closing of channels, as well as reading and writing to and from them, and we can destroy principles and objects. So during each of those operations, the label sets of the involved parties might or might not have to be updated. For example, if you open up an object for reading, which the notation here is that the information flows from the first parameter to the second. So open OP would be opening the channel for reading, so P can read from O. So if you do that, then you need to update, for example, the principles label set with the objects. But the objects label set is not affected at all because nothing has happened to the contents of the object yet. If you write to a channel, for example, nothing happens if it's a channel between principles, because the channel gets the label set of the writing process, but the other principle is not updated yet because it's an asynchronous operation, and you're basically writing into a pipe, and only when that information is read again, we update the label set of the second principle. And probably this example is going to make it a little bit clearer, and I hope that that gets recorded okay. So we have this set of operations here. We have an initial state with 4 principles. First, P1's label set is A, P3's label set is B. Plus we have one object on the system whose label set is C. And as my update function, I'm simply using the label, the set union operator. So we're just unioning labels as we go along. So we have the following operations. Principle 1 creates an object O2, at which point O2 inherits the label set from its principal. Then a write channel is opened and data is written to that object, and the channel is closed. Now P2 opens a reading channel to the object 2, at which point P2 inherits the label from the object, label A. And he reads opens the channel, reads from the object, and closes the channel. Then P1 gets rid of O2, so there's no more O2 on the system. Now P2 creates a new principal who inherits the label set of P2, which is A. P5, the newly created principal, now opens object O1, who had label set C and therefore inherits the label set, reads data, closes the channel. Now channel between process P3 and P5 is opened. So P5 also inherits label B from P3. P3 writes some data to P5, which P5 then reads, and then the channel is closed. And finally, a channel between P5 and the principal P4 is opened, at which point P4 inherits all the labels from P5, and data is written to P5. So you might say, big deal, what does that all mean? So, and just to make sure I don't screw this up, I have it written down here somewhere. If you go through this again, we could see these as processes on a system. And in operations 1 through 4, O2 is created, which could be a malicious script, which P1, who might be a malicious user or process on the system, generates. And then in operations 5 through 7, somehow tricks P2 into executing the script. Operation 8, P1 gets rid of the evidence by deleting the script. And operation 9, maybe the result of executing the script, P2, who may have privileged was it privileged runtime who may have super user privileges, let's put it that way, spawns a new process, who then, in the next operations, executes another file that was left there on the system by maybe some other malicious person or who knows what. And then receives some information from P3 upon which he performs some bad things to P4. So if you interpret the labels, the A, B, C, maybe as some sort of location information, then when examining the system and you have P5 still running, you have a notion of which locations actually played a part in this. Plus, P4 also receives this information and then maybe can make some conclusions from that. So in order to make any statements about my model, I had to extend it a little bit. And basically, I partitioned the set of principles on a system into those that can inherently generate a label and those who can't. And if there's more than one of such groups, then basically I require that you are able, by looking at the label, to say which group did it come from. Plus our label update function must actually preserve the labels that we are propagating. And in the example, I used the set union already. Plus I'm defining what I call a potential information exchange path between two principles on a system. And as an informal definition is, we have from this sequence of the total operations, this is a subset of those operations that directly lead to information being passed along. So it could be P1 writes to an object, another principle reads from the object, and then that principle finally communicates with P2, and that's the direct chain of how the information was exchanged, or potentially. Because remember in the beginning with undecidability, this is how information could have flown on the system. And basically, I require for that information exchange path that the read and write operations add up, meaning that if there's a channel open between two principles and there's already data in the channel before we write again to the channel with a different label set, then all that previous information has to be read before the new label set gets updated with the principle through the read operation. And given these extensions to the model, I can give you these two properties, and the third bullet is just a direct consequence of that. So if a label is bound at a principal P1, and there exists a potential information exchange path from P1 to P2, then the label will be present as part of P2's set. Furthermore, if you find a label at P2, and P2 is not a principle that could have generated this label itself, then information must have been exchanged between P2 and a principle who could have generated this label. And as a consequence from that, we can see the absence of a label as a guarantee that no information was exchanged between a principle that could have generated a label through the channels that are supported in an actual implementation, and not considering covert channels. So quickly, two case studies. One is user influence. So we take the system processes as our principles, and all the shared resources on the system are our objects. These are files, logs, global variables, whatever you have available on the system. The label set is actually the set of user IDs, which is a fixed size on a system because user IDs, I think they're bound at kernel compilation or something, the number. And the actual binding of the label takes place when a user logs in through there are various programs who can do that, but usually it boils down to just a system call, setuid on Linux or setlogin on the BSD family. So basically the group of principles who can generate a label is limited to those who provide a login. Second case study, origin information. we have the same subject world as in the previous example, processes on a system and shared objects. But the labels now need to uniquely identify the source of the connection. And this could be a network identifier. You can use the source port, destination port, and source addresses for TCP and UDP. Or you can even think of using information such as GPS information to convey origin here. And the binding in this case takes place when you accept data from a network. And this would be for TCP, the accept system call, or receive from for UDP. And this actually poses a problem for the current way that servers operate. Because the current way is you have a server who listens on a port, then the connection is accepted, then the server forks a child process who handles the connection. And if we do that, then each time the server accepts a connection, a label gets bound to the server process. So it's very likely that this needs to be changed so that we can have an atomic accept, fork, and bind label to the child in order not to clutter up the server process with too much information. I'm currently working on a proof of concept implementation by modifying the FreeBSD 4.12 kernel. I have a fixed set of possible labels. I'm primarily focusing on user IDs right now. We have a global table of what the labels are, and we only need to store a small vector of labels directly in the process table. So these are just, it's a bit vector of what's there. Files are stored in a special file, which means we have them all in a central location and can easily determine which file has which label and also which label is contained in which files. The disadvantage of that is an added overhead when actually doing the updating by having to access the file. And for the update function, we only need to bitwise ORing all these vectors in order to make the updates. Modifying system calls for the open, close, read, and write instances for both sockets and files, and I think pipes are actually a subset of one of these two. The user information, as I described earlier, is bound at the set login system call, and the network information at accept and receive from calls. Other applications of this work, other than the forensic information I mentioned earlier, is network traceback, especially in conjunction with the network identifiers. But you can use labels for access control as well. You can say, similar to the owner group world permissions you have on a system, you can certainly group locations together as well, location labels, and have local, a group of friendly locations and world permissions for files, for example. Further, you can probably use labels for system administration by identifying certain processes on a system that you don't want to have certain labels, see how things actually flow on the system. Plus, you can use the information for intrusion detection as well. In conclusions, much of the desired information is currently not present or recorded, but we can probably make a lot of this happening depending on what your space considerations are. And especially process labels can help generating some of the desired information, especially with the examples of user influence and location information. And I've demonstrated where else this work might be useful. So limitations, I've already mentioned a few of them. The first one, for example. The second one it might be necessary to introduce no label flags for special files. Otherwise, the accumulation of labels for a process might be just too much if you never lose any labels. And this might be files that are written at the end of a login session and then accessed again at the start. This could be very hindering in capturing only the labels that were accumulated in a session itself. Plus, actually using processes might be a little bit too broad, especially for platforms that have many users who open up one session and then work in there for 8 hours and then do everything from one session. I would expect that a lot of labels will be accumulated. So you might actually try to find something else that fits it better, some sort of context based on maybe which user agent is executing at the time and associate the labels with those. Plus, location and peer-to-peer networking probably is not a good idea, because if you download a file from 1,000 different sources, it would have 1,000 labels associated with it. So right now I'm probably aiming more at server systems that provide services to the system, where you really don't want any user action, and anything that bypasses the server by some sort of exploit is bound with the location. And then if the system activity is there with those labels, that would be a more appropriate thing to notice than trying to track the location of a system with people running peer-to-peer software, for example. Remaining in future work, I need to finish my proof of concept implementation and do a performance analysis, and then determine actually what is a good balance between the number of labels I allow on the system versus the usability of that system. Because at some point, I haven't talked about space consideration, but if you run out of label space, you have to make a decision on what you want to do. You can either drop labels, which is not good from a security perspective, or you can deny operations, which I think is the more secure way to go. But this will break things on a system. So basically, you need to determine what are the label requirements of well-behaved programs and make a decision on that, and where you set that threshold. How many labels do you allow a process, for example? Another interesting thing might be label propagation across a network. This way you could have true network traceback, meaning you have at some host where a user actually is located and sits and then does some stuff, and he logs into a chain of hosts to launch an attack. You could use labels to actually propagate the original location information for that. Can certainly incorporate labels into access control, and I think those two actually go hand in hand if you want to go for a secure system that does support labels, meaning that certain processes with certain labels should not have access to everything. This way you could, for example, limit the rights of the root user if they carry some foreign label. That probably is not a good idea, and you can perform access control right there on that. And finally, I've talked about introducing a lot of extra data to a system, quite a bit actually, if you take into consideration of that we potentially log every file operation now. How can we actually process and analyze all this extra information that I'm suggesting here? And this concludes my talk. Are there any questions? Yes.
Question for how can where did you store the vector for files? So store the labels for the files.
Right now, I am storing them in a special file itself, and I probably want to move to actually pushing that into the metadata of the file.
I'm curious, for the regular file system, does the metadata have extra space to store the labels?
What file system is that?
In any common regular file system, like ext2 or 3, is there any extra space to store the labels, or you need to modify the file system?
Yes,
Add a
file
new-
systems will have to be modified if I want to store them with the file directly. But right now I'm storing them just in a file. It's a mapping. It's a file name vector mapping.
Okay.
And it's just a proof of concept implementation. If you wanted to modify the file system, you could either see if you have some leftover space in an inode somewhere, which is very unlikely. You probably have to dedicate an extra block and do it that way.
But suppose you just have for a label with only fixed space, maybe suppose have only 32-bit.
Yes.
Maybe this is reasonable.
Well, 32-bit might not buy you a whole lot, but
Yes, yeah.
so but yeah, you'd have to see where you can find space. Okay. Any other questions? Well, then I thank you very much.
Everyone get sign the sheet.
I work on very similar idea.